Hello and very warm welcome to the channel. First, I would really like to thank all of you guys for supporting the channel, for subscribing it, and I'm very grateful that many of you are sharing it and we are growing very rapidly. So much appreciated. I am very indebted for all of your support. Now in this video, I'm going to share something which is quite interesting and quite realistic too. You know that I already have covered heaps of models on the channel in the last few days, months, and year, and there are few models when you come across them, you really stop in your tracks because the model seems a bit different, such as this one, InternLM Step Prover. The model is interesting because it deals with something which is quite near to fundamental truth, and that is the math theorem. Math theorems are rigorously proven statements that establish a fundamental truth or relationship within a mathematical framework, and that provides the foundation for further mathematical exploration and application. I believe that all of this scientific development and everything stands on the foundations of mathematics, which is centuries old, and the mathematics stand on the foundation of theorems. So what this model does, it primarily works on Lean-Github and multiple synthesis data set to achieve state of the performance on few of the benchmarks which show math proving or theorem proving ability in multiple domains. And I will show you after we install it locally on our system, and then we will play around with few of the fundamental mathematical theories. We will ask you to prove some of the theorems. Before I do that, let me also tell you something about a very interesting concept which is called as lean. Now, if you go through the model page, you will see one of the examples they have shown is this. Just look at this example. It might seem like a cryptic something, but it's not. This is a language which is called as Lean, Lean. Lean is a theorem prover and proof assistant that allows the users to formalize and prove mathematical theorems using a high level declarative language. The syntax and notation used in this example with are very uh, in line with Lean language. So you see in this one, these are the keywords DECL and goal, and then we have this proof step keyword. We also have used mathematical notations like static and this um, caret sign and few others. And then we have also inductive proof structure such as n with tht. So what this code is doing here. So this is an example input and output for a theorem prover or proof assistant, specifically in the context of formal verification or mathematical proof. So first line here, this one as an input, this is declaring a theorem or lemma named mul underscore POW in the mynat namespace. That is all it is doing. Then this is the goal which specifies to be proven, that involves variables a, b and n of type capital N, which is a natural numbers by the way. And then we have this long line. This is a statement which is an equality involving exponentiation and multiplication. So it seems quite cryptic, but this is a theorem. And then in the output, this is the first step in the proof, and there will be a long line of proof, but they are just displaying the one line here. So for example, this induction n, this indicates that the proof will use induction on n, and then with tht, this introduces a new variable t and a hypothesis ht, which will be used in the inductive step. So all in all, the input example declares a theorem and specifies the goal to be proven, while the output example provides the first step in a proof using mathematical induction to establish the desired equality. So this is what this model does. So we will see after installing it we will provide a different thing, and I am sure you will enjoy it. So InternLM Math has done really good stuff with prover. We have already covered few of the InternLM Math, but this one is a step prover. You already know what prover is, what is meant by the theorem steps. Okay. Now, before I move forward, allow me to give a huge shout out to our good friends at Mast Compute who are sponsoring the VM and GPU for this video. If you're looking to rent a GPU on affordable prices, I will drop the link to their website in video description. Plus, I'm also going to give you a coupon code of 50% discount on range of GPUs, so do check them out. This is my Ubuntu 22.04 system and this is my GPU card where I am running NVIDIA RTX A6000 with 48 GB of VRAM. Let me clear the screen. And now first up, what I'm going to do, I'm going to install a Conda environment which will keep everything separate from my system, and then we will proceed further. And by the way, I will be installing the model and playing around with it in the Jupyter notebook. But before that, let me install all the prerequisites like torch, Hugging Face Hub, transformers, and then we will install the Jupyter notebook and then launch it in the browser. So let's wait for it to get installed. So these prerequisites are done. Now let's install Jupyter notebook, and this is going to launch this Jupyter notebook in my browser. So let's wait for it to get launched. Notebook is launched. Let me import some of the libraries which we have just installed. So I am importing torch transformer. That is done. And now let's grab our tokenizer and model. And we are just going to download it from Hugging Face. So you can see that it is InternLM Math 7 billion, and it's a 7 billion model, by the way. And I'm just downloading it in float 16. You can go with float 32 if you like, but I just want to keep it that way. And then we will be evaluating it just to see what exactly is in this model. And the model download is in progress. As you can see, there are 8 shards and around, I think all of them are around 2 gig. So make sure you have 16 to 17 gig of space available on your local system. Let's wait for it to get downloaded and present on my system. The last shard is being downloaded. Should be fairly quick now. And the model is almost loaded to my GPU, and that is also done. Let's just go up and check because it is, yep, that's all done and good. And now let's do the inference. So in the first prompt, what I'm doing here is, as you can see, I am checking group theory theorem, which is mainly related to associativity. So in this one, we are proving that associativity is crucial in a group theory, ensuring that the order of operation doesn't change the result. So let's run it and see what model does here in terms of proving it. And there you go. So model has come back with apply add assoc. So good thing is that model is so intelligent that it identified that it is a group theory, and add assoc in group theory is a common proof step to invoke the associativity axiom, which states that for any element A, B, and C in a group, the following equation holds, which model already identified in the third line of the prompt. And by applying add assoc, the model is essentially saying, hey, I can use the associativity property to rearrange the terms and make progress in the proof. So really well done model. Let's try out uh, the next one. And in the next example, what we are going to do, we are going to check ring theory. So let me paste the ring theory here. Okay, so this is a ring theory, which is a distributivity property in ring theory connecting addition and multiplication. So let's see how it does. So let's wait for it to come back. There you go. And this output really demonstrate that a model has a solid understanding of ring theory properties. So what this line is doing, this is a sequence of rewriting steps using various ring properties to transform the original expression. And what it is doing here is it is removing unnecessary multiplications by 1, and it is applying the distributive property to expand the expression. And likely model is trying to put the expression into a more suitable form for further proof steps or to reveal a hidden structure. So really awesome stuff here. In the next one, let's try to see if it knows about field theory. Now the field theory, what happens in field theory is that power addition is a key concept in this theory, allowing for the combination of exponentiation and addition. So let me run it and then we will see how it goes. There you go. Now, this output clearly shows that model has a solid understanding of mathematical induction in the field theory. So if you look at this output, this is a proof step that uses mathematical induction to prove a statement about all natural numbers n. So induction n starts induction process with n being the induction variable, and with n this one with n this specifies the induction hypothesis IH to be used, this one, and then IH refers to the induction hypothesis itself, which is assumed to be true for some n numbers. So model is essentially saying here that I will prove this statement by induction on it, and I'll assume it's true for some n. And if you just keep doing this, model is going to produce the whole theorem and prove it. It will prove it. So all in all, you can see that the model's capabilities are really amazing and simply awesome. I mean, I could go on and on with this model, but if you're from maths background and if you really appreciate the maths beauty in everything universal, you would know that this model is really a sweetheart. So that's it, guys. I will drop the link to it in video's description. Let me know what do you think. If you like the content, please consider subscribing to the channel. If you're already subscribed, please share it among your network as it helps a lot. Thanks for watching.